So now that we have the cost for logistic regression, we want to find out how should we update the value of our parameters. And so this requires a little bit more complicated calculus, but we can do a quick derivation. So let's say this is we're going to calculate this for one example, but remember, all you would have to do to extend this to more examples is just add this term for all of the examples and then divide by the number of examples that you have. Essentially take an average across all of the examples in your data set. So we have J is equal to negative of y log y hat plus 1 minus y times log of 1 minus y hat. And so let's say y is let's say what we're going to do. Oh yeah, we were going to find the derivation for dj dw. Just like last time, remember we want to do w equals w minus alpha times dj dw, right? This is the original value of w gets replaced with the original value of w gets replaced with whatever the value was minus alpha times the slope of the cost function at the point of w. And remember, minus is because we want to go in the opposite direction. If the slope is positive, we want to decrease the value of w in order to decrease the value of j, the cost. And if the slope is negative, we want to increase the value of w in order to decrease the value of the cost. So we want to apply that negative sign. So the update function is the same, exactly the same in representation, but this, how you find this out is different for logistic regression compared to just normal linear regression. Okay, so you have this right here, which is y hat. And remember, y hat is sigmoid of wx. And so in terms of the chain rule, I just want to let you know that, and if you don't know about calculus, it's okay, you can skip this part. But the derivative of the sigmoid function with respect to whatever its input is going to be the sigmoid function. It's actually very simple. It's the sigmoid function multiplied by 1 minus the sigmoid function on the input. So actually, whatever your output is of the sigmoid function, just multiply that by 1 minus the output. And that's how you get the derivative. And you can derive this yourself based on whatever the definition of sigmoid was, right? So sigmoid of x is equal to 1 over 1 plus e to the power of negative x. And you can derive how this would be true, but I'm going to gloss over that a little bit for now. And I'm going to go on to trying to find out what dj dw is. So I'm going to take the derivative of this with respect to w. Now y in this case would be considered a constant, and we can have log. The derivative of log is just 1 divided by whatever the input was, right? So in terms of this first term, so if I actually get rid of this negative sign, I put this here, negative, and I put this here. So now we can just focus on this first term. We take the derivative of that with respect to w. Then what would happen is negative y times 1 over y hat, which is actually sigmoid of wx, times the derivative of this with respect to w, right? Which would be the sigmoid of wx times 1 minus the sigmoid of wx. And then all of that multiplied by x, because the derivative of wx with respect to w is just x. And now Now that's the first term, right? And then I think the second term would be something similar. The second term would be something similar like negative 1 minus y times 1 over 1 minus sigmoid of wx times times now we would have like a negative 1 in here, and then we would have a sigmoid of wx, and then we would have 1 minus the sigmoid of wx, and then we would have x at the end. So you can go through all of these and verify them for yourself. I think this should be correct. But this would be this would be dj dw would be this. Now over here, I want you to notice that this actually cancels with this. So we would end up having negative y times 1 minus 1 minus this, this is y hat actually. So 1 minus y hat, and then times x minus, and so I'm going to start with the second term. So this actually will cancel with this, and you'll get and then this, there's a negative sign here, but there's also a negative 1 here, and then there's a 1 minus y here. So there's like three, so there's two negatives, I guess, and so those will kind of cancel out. But if I want to have a negative here, I can just have a y minus 1 over here. Okay, so that ends up being the same thing. And then times this, which is just y hat, and then times x. Okay, so you can notice how, I guess, I'm going to remove the negative. So y times 1 minus y hat, and then times x plus y minus 1 times y hat times x. And so you can sort of appreciate some of this symmetry that's going on here, I guess. There is y here and 1 minus y hat, and then there's y minus 1 and then y hat over here. So it's kind of almost like the reverse. And this is dj dw. This is the derivative of the cost function. Only for one example. We've only used one example from our data set in here, but with respect to w, and that would give you the slope of the cost function with respect to w at that value of w, and it would tell you, should you increase the value of w or should you decrease the value of w? And by knowing that for one example, you can calculate that for all of the other examples. Take the mean, right? Take the mean of all of the updates, and then you would be good to go to know how to update your function or update the parameter w. And all you would do is you would follow this. You would replace your value of w with your old value w minus your learning rate alpha times dj dw. It just occurred to me one more thing, which was the fact that when you're learning for the value of alpha, right? This is totally unrelated to the topic, I guess, of this video, but for like the last video, I was talking about how the value of alpha, if it's too small, then you'll take too long to converge to what you want your value of w to be. And if you have your value of alpha too big, then it will basically go, it will go too high, right? And it will update too much, right? And it might overshoot and start to diverge instead of converge. And it just occurred to me that I want to explain why, if you choose your value of alpha to be 0.1, and it's a good value of alpha, at least initially, it should remain a good value of alpha for at least for some time. It should not start to like overshoot just because you're very close to the minimum over here. And that's because the update is actually the slope times the value of alpha. This is the magnitude of your update, how much you're updating by, how much you're updating your value of W by. And so let's say you're here, right? And you make this update, and now you're over here. Well, the value for the slope at this point versus this point, they're actually both negative, but this, let's say, might be -5, and this might be -2. The value for the slope, the magnitude of the slope, keeps on going down. And so even though, let's say this is fixed, right? This is 0.1, we fix it throughout the duration of training our machine learning model. Even though this is fixed, this will continue to decrease as you go closer and closer to the minimum. And if you're very close, then the slope of that line will basically be 0. And this term will essentially go away. And you'll essentially be replacing W with its old value of W, and you'll stop updating as much, at which point you can sort of stop your training. And so you can stop your training at one of 2 points. Either when the cost is low enough that you're happy with your model, or more likely when you're done training, which is when you've converged to a point and your loss doesn't seem to be decreasing anymore, and the value of your update is too small to actually influence the value of anything. So you could set a threshold. You could be like, if the magnitude of my update is below this threshold, then I'm just going to stop training, right? And so throughout the training process, the slope will decrease, and that's just another thing I wanted you to know. But I guess the main point of this video was to derive the cost function for the cost function update for logistic regression. And then going back to what I said initially, you just guess, and then you evaluate, you guess and check method, right? Where you guess your initial value of W, then you evaluate that, then you update that in the direction it needs to be updated in. Does it need to be decreased or increased in value? Then you repeat that again and again. And then this together is called gradient descent, right? And then that's a gradient descent essentially for logistic regression. All of the same steps. The only difference is the cost function we used and then the update that we used. So the DJ DW, that needed to be derived because the cost function was different, and because the formula for y hat was different in that case. Oh, oops. But I guess that's sort of the summary of the video. So thank you for watching.